Wow, lucky. Oh, Jesus. Bro. I see, I did laugh one. I need to go.
Why you call me?
I did go. Oh, Jesus. I think the now people now. Hello everyone, we are live and we are about to start. Yeah, thank you for those that are just joining us. I'm about to start. I'm just trying to spread the link to as much persons as possible. Hello everyone, you are welcome to Warren Science Academy. This is the day 2 of our 2026 Jamb and WAEC Chemistry Masterclass. And I welcome everyone, those who are just joining the live and those who are yet to join this live class. I welcome you specially to the day 2 of this class. And in the course of this class, we are going to look at a very important and essential topic in chemistry, which is gas laws. So I urge you to pay attention and also do it to get the right material, as this topic involves series of calculation and theoretical aspects. So in the course of this video lesson, we are going to look at gas laws, and in the course of this topic, we will look at the behaviors of gas or their properties, and then we'll look at the series of gas laws we have in chemistry. So do it to pay attention and do it to get the best out of this class. So we'll begin the video lesson by looking at what we call gas laws. Now, why are they called gas laws? So we have two words present in this topic, gas and then laws. So let's go. In the beginning part of chemistry, we have what we refer to as matter. And what is matter? We define matter as anything in nature that has mass, not weight please, mass and occupies space, because there's a difference between mass and weight. There's a key difference between these two terms. They are not similar in any form. Mass is different from weight. We'll talk about this in some other video. But when we talk about matter, matter is anything in nature that has mass and also occupies space. Occupies space. So this is the basic definition of matter. So matter is simply anything in nature that has mass, again not weight, and occupies space. And then matter can exist in three forms, or the three states, which we refer to as the three states of matter. And those three states of matter are solid, 2 we have liquid, and 3 we have gas. So today we are interested in this third form of matter, or this third state of matter, which we call gas. Now, what is so special about gas that we are looking about it as a topic on its own? Now, gas has some properties, it has some behaviors which make it different from liquid and which makes it different from solid. So gas is simply a state of matter in which the particles are not held together by any closed force and they are free to move about. So that's the basic definition of a gas. So it's simply a state of matter or a form of matter in which the particles in the sense that what makes up this matter, they are not held together by any strong bond or by any strong force, and they are free to move about. Now let's take a good example. Let's say we have a family. In the family, father, mother, and children, and there's no love between these persons. There's no love between the father and the mother, between the mother and the children, between the father and the children. So when there's no love, the children, they just tend to what? Move about. That is the singular reason why if you take a gas molecule, let's say I take a gas now, let's say perfume, a good example, I spray it at this edge of the class, the particles will tend to spread around this entire vicinity or this entire surrounding. So for gas particles, they have this special behavior because of the way the particles are arranged. So the particles are not held together by any strong bond. They are just free to move about. Next, in this topic, we have what we call law. So we have defined a gas. So a gas, simply, gas is the state of matter. Is the state of matter in which the particles are loosely held, or the attractive force is negligible. So this is simply the state of a gas. So two things, the particles are loosely held or the attractive force is what? Negligible. Negligible means it is as if it is not there, like it does not exist. So that's what makes up a gas. Now, what is a law? We are not interested in a law. Now, in science is simply a series of knowledge that go through certain steps. Like in science, you don't just come up with something and you just say, oh, A plus B is C. No, we should know why A plus B is C. So in science, whatever we have seen or whatever we believe that, oh, it is true, we must take it through series of steps. And at the end of that day, it's going to end up becoming what we refer to as a law. Now, let me give you the basic steps. Now, we have, in science, every scientific process begins with what we call that process what? Scientific method. We refer to this as what? Scientific method. So scientific method is just a series of processes through which a knowledge must go through before it becomes acceptable. So we cannot just say, oh, A plus B is C, and everybody just says, oh yes, we are accepting it. No, we must go through some process like experiment, testing, and series of things for to now believe that, oh, this is actually true. So in science, we have what we call a scientific method, and every scientific method, take note of this, begins with what we refer to as an observation. Observation. So there must be an observation. You must observe something. Probably I see that, oh, if I throw things up, they will tend to fall down. That's an observation. Then we now start to ask ourselves, why? Is it that there's a force? Is it that there is a barrier or there's a resistance? So a series of questions will come out. Now, what will that lead us to? It will lead us to what we call an hypothesis. Hypothesis. So hypothesis, as it is defined, is a reasonable explanation for any observed phenomenon. So a reasonable explanation, something that is reasonable. So if I take a mark and I throw it up, and I found out that, oh, when things go up, they tend to come down, I can say, oh, probably there's a force that attracts things down to the earth. Not I will say that, oh, the marker is not well fed. That's not reasonable. So an hypothesis is simply a reasonable explanation for any observation. Then from hypothesis, it leads to what we call an experiment. Experiment. Now, so that thing we have found and we have given an hypothesis, the next thing we have to test it. So when we test it, and if we find out that it is true, if we find out that, oh, what I've said earlier is true, it then becomes what we call a theory. Then we have to test it further. So on further testing or further experiment, if it is true beyond any doubt or beyond any limitation, it finally becomes a law. So it is the law we are talking about in the course of this class. So a law is simply a principle that is true beyond doubt. So we have tested it. We've tested it in Nigeria, we tested it in, let's say, a European country, an Asian country, and we found out this is true beyond any limitation or doubt. It then becomes a law. So the end process of every scientific method, we end up at a law. So that's what we call a law. So now we now understand gas law. So what is gas law in general? So let's take down that definition. So for gas laws, we have gas laws they are physical laws. They are physical laws that describe the relationship. Between the pressure, temperature and volume of gases. So generally, when we talk about gas laws are laws. Already we have established what a law is. It's simply any principle that is true beyond any limitation or any doubt. Now, there are laws that describe the relationship. Now, there are three major things we use to describe gas, though there are more than these three things. They are the pressure, temperature, and volume. So now the various gas laws we are going to look at in the course of this class will tell us the relationship between pressure, temperature, and volume. Probably if we increase temperature, what will happen to the pressure? Or if we increase the pressure, what will probably happen to the volume? So this is what gas laws they define. And just to add something, gas laws define one particular type of gas. So let's take that. So gas laws are used to describe ideal gases. Now, this now brings us to an interesting concept, which is called ideal gas. So gas laws are used to describe what we call ideal gas. Now, if we say an ideal, that means there is something else which we call real gases. So the opposite of ideal becomes real. Now let's explain. So we have real gas versus an ideal gas. Now, what is the difference between these two concepts? Now, this one question you could be asked. Real gases describe dash. You could be given A, ideal gas, B, real gas, and probably other options. Real gases or gas laws rather, that we'll talk about describe what we call an ideal gas. Gas laws do not describe the real gases. Now, let's look at something. I want to talk about real, I want to talk about ideal. What do we mean? Now, it's just like a man wants to get married, and the man says that, oh, the woman I want to marry should be this, she'll be that, she'll be able to cook, she'll be able to do that and do that. Now that's what is just in the imagination of the man. The man thinks that, oh, the man should be beautiful, should be this, should be that, and the man sees so many pictures of the woman he just wants to marry. But later on in life, he might end up probably marrying the woman, and probably the woman could be able to do so many things, but something would just be missing. Now, that woman that was in the mind of the man is an ideal. So ideal means in the imagination. Then whatever we see or whatever exists is what we call real gases. So the difference between real and ideal gas is that real gases are gases in nature or in existence or in reality. But ideal gases, they exist in the imagination of scientists. So now, scientists are able to create laws that we follow their various laws. So they created laws that we behave or that these gases will obey. So ideal gases, they obey the gas laws, but real gases, they do not obey gas laws. Now this brings us to a very important question they could ask in the exam. So all the various gas laws which we'll talk about today, they are obeyed by the ideal gases. Boyle's law, Charles' law, general gas law, Dalton's law of partial pressure. All the various laws we'll talk about, ideal gas obey them, but real gases do not obey them. So when we talk about gas law, they describe ideal gas and not real gases. Now, but that is also a very important question which they could ask you in your exam. Under what conditions can real gases be made to behave like ideal gas? This is a very important question in exam. They could ask you, under what condition can a real gas be made to behave like an ideal gas? And how do I remember this? I created an acronym which I call the LOT heap. L-O-T, LOT heap. So under a low temperature and a high pressure, we can convert a real gas to an ideal gas. So take note of these two conditions that a real gas can be made to behave like an ideal gas. The two conditions are under low temperature and high pressure. High pressure. So under these two conditions, we can convert a real gas to an ideal gas. Then in the opposite, when this opposite takes place, the ideal gas will return back to a real gas. So if we increase the temperature and if we reduce the pressure, this ideal gas will be converted back to a real gas. So in low temperature, this guy will go to an ideal gas, and also under high pressure. So to remember in the exam, you could be asked under what condition will the real gas be made to behave like an ideal gas? Simply remember low heat under low temperature and then high pressure. Don't forget that. Now let's move on. Now when we talk about gas, there are many things we can use to describe a gas. We call them the properties of a gas, and we're going to talk about them in the course of this class. So let's go. So the properties of a gas. So we'll talk about them before we talk about the various gas laws that we have in chemistry. So properties of a gas. So properties of a gas. Properties of a gas. So properties of a gas. Now, what are the various properties of a gas? We basically take just 5 of them. Number 1, we have what we call pressure. Pressure. Number 2, we have what we call volume. Number 3, we have what we refer to as temperature. Number 4, we have the fourth one we call the amount, or basically we call it we measure amount with mole. And lastly, though it's just a derivation from this, though which we call molar volume. Molar volume. Just a derivation from volume. So I just have to pick it out so I can talk about molar volume specially. So now we look at these 5 properties. The first one is what we call pressure. Now what is pressure? Now pressure from our basic physics is the force exerted per unit area. So for pressure in physics, we define it as the force exerted per unit area. So it's simple. This is a board. This is my hand. If I place my hand on this area of the board, I'm exerting a force. There's a force here on this area. So around this point, there's a pressure on this area. So that pressure is what is being defined as the force exerted per unit area. So there's a formula for it, but that's not of interest to us. What we just want to know is how to convert pressure from one form to another, or from one unit to another. Now I will urge you to take note of this conversion factor I'm about to drop. Now in converting of pressure, this is what you should know. 1 atm, which we call atmosphere, is a unit for measuring pressure, is equal to what we call 1 bar, is equal to what we call 760 millimeters of mercury, which is equal to 760 torr, which is equal to 101,325 Newton per meter square, which is also equal to 101,325 Pascal. So this is the conversion factor. For those players that are writing advanced exams like the UTME and the SSC, I will urge you to take note of this, because most persons are familiar with ATM, millimeters of mercury, and then Newton per meter square. Now some other units which you might not be familiar with are bar and then torr. So take note, 1 atmosphere is equal to 1 bar, is equal to 760 millimeters of mercury, and is equal to 760 torr, which is also equal to 101,325, which some books might just take in the index form as 1.01 times 10 raised to power 5. They are just the same thing depending on whatever you are given in the exam, in Newton per meter square or in Pascal. So we are going to solve a question. So let's say in an exam, we are learning this because why are we learning this conversion factor? In an exam, you might be given a question, and the question might be in, let's say one part of it might be in millimeters of mercury, and the other could be in atmosphere. So we cannot work with millimeters of mercury and atmosphere, so they are not the same unit. So we have to convert one to the other so that we can easily solve. Because in solving of questions, your unit must be the same. If you are working with millimeters of mercury, ensure that you are working with it all through. If you are working with Pascal, ensure you are working with Pascal all through. So don't use Newton per meter square on one side and then you are using ATM on the other side. Ensure that your units are the same. So let's take a question in an exam. So let's take a question. Question 1. So let's say we are told to convert 2 ATM to millimeters of mercury. So it's just a simple question. So let's say we have ATM and we have 2 ATM. I want to convert that ATM to millimeters of mercury. What I'm going to do is a simple process. You come to this your conversion factor, which you already know. So in our conversion factor, we are interested in atmosphere and millimeters of mercury. So I'm going to come to atmosphere, and then I'm going to come to millimeters of mercury. So from this conversion factor, I can now see that 1 ATM is equal to 760 millimeters of mercury. So I have 1 atmosphere to be equal to 760 millimeters of mercury. But I'm to convert 2 ATM to millimeters of mercury. So what I'm going to do, so 2 ATM, we are going to put ATM under ATM and millimeters of mercury under millimeters of mercury. So this is equal to X. So then we'll cross multiply. And when we cross multiply, 1 times X will give us X. Then 2 times 760 will give us 1,520 millimeters of mercury. So this is how we simply convert. So you can basically convert anything. I can convert 1 bar to Pascal. I can convert 1 ATM to Newton per meter square, provided you know this conversion factor. And the conversion factor is everything you have here. So with this conversion factor, you can simply convert from one unit to another unit. So we move on to the second one, which is volume. So the second principle which we have, or the second property of a gas, which you ought to know, is what we refer to as volume. Now what is volume? Now volume is just simply the space occupied by the gas. Simple. So volume is the space occupied by the gas. And when we talk about volume, it's just space. In mathematics, volume is calculated as length times breadth times height. So this is how volume is calculated. So the entire space For example, your gas cylinder is a good example. You have a gas cylinder. Within the gas cylinder, there is a space. That space, the gas you occupy, is what referred to as the volume of the gas. So now, in calculating of volume, there are units. There are so many units. We can measure volume with liters. We can measure it with dm cube. We can measure it with cm cube. We can measure it with mm cube, meter cube, so on and so forth. So now, how do we convert? That's very important to us. So there are basic units you must know. So 1 liter, which is the commonest, liter is the commonest unit for measuring volume. 1 liter is equal to 1 dm cube, which is equal to 1000 cm cube, which is equal to 10 raised to the power of minus 3 meter cube. So ideally, we ought to know this. So this is the basic units we have for volume. So in exam again, you could be given liter and cm cube. So I cannot work with liter and cm cube. So ideally, I have to convert one of them, either liter to cm cube or cm cube to liter, so that I will ensure that the units are the same. So let's take a question and just know how we play with this. So let's say question 2. We are told to convert 22.4 dm cube to cm cube. Let's see, we are suspect to do this. So it's simple. Again, come to your conversion factor. From our conversion factor, we know that 1 dm cube is equal to 1000 cm cube. So I'm going to pick that out so I can solve. So we now know that 1 dm cube is equal to 1000 cm cube. So we are going to convert 22.4 dm cube. I'm going to place it under. So I have 22.4 dm cube to be equals to x, because we don't know what it is in cm cube. So then we cross multiply. 1 times x is x, and then 22.4 times 1000 equals 22,400 cm cube. So by so doing, we are able to convert 22.4 dm cube to centimeter cube. So if you have any question at this point, go ahead to leave it in the comment section just beneath this video lesson, as I will go back to the video lesson and get the comment and then respond to them. And also, if you are new here and you haven't subscribed to this channel, you can do me a favor by clicking the subscription button just beneath this video lesson, and I will really appreciate that. So we'll come back to the video lesson. So our third parameter here, or a third property of a gas, which we have, is what we call the temperature of a gas. Now, temperature, as we all know, is what we refer to as the degree of hotness or coldness of a body, but that's just a very basic and light definition. Now in chemistry, how do we define temperature? So let's go. So we'll take this off the board again and then we'll talk about temperature. So for temperature in chemistry, it is defined. So temperature is defined as the average kinetic energy of the particles of a body. So when we talk about temperature, already or basically, whenever we have to talk about temperature, we define it as the degree of hotness or coldness. So how hot or how cold the body is what we refer to as temperature. But on an advanced level, which we ought to know, temperature is defined as the measure of the average kinetic energy of the particles of a body. Now, so you just want to talk about kinetic energy. Kinetic energy is just energy in motion. So just imagine you running or you jogging, and then you start sweating, your temperature will rise a bit. So it's just how the kinetic energy of the particles of your body are at that moment. So a measure of it, a measure of the average, is what we refer to as temperature. Now, just to add something to this video, when we talk about the average kinetic energy, it is temperature. There's what we call the total kinetic energy of a body. So the total kinetic energy of a body is what we refer to as heat. So the difference in the definition of temperature and heat is that temperature is the measure of the average, then heat is the measure of the total kinetic energy of the body. So basically, again, when you are running or you are in motion, there's a tendency for your body to generate heat, and when it does that, there's a tendency for the temperature to increase. So if there's a drop in heat, there will be a drop in temperature. So they just go side by side. So now I want to talk about temperature. What are the units? We have what we call Kelvin. Kelvin. Now Kelvin, the symbol is K. Now some students do make this mistake of writing degree K, which does not exist. Kelvin is just simply K. Then we have Celsius, or what we call the centigrade scale. The centigrade. And this is measured in degrees Celsius. Then we have the Fahrenheit scale. We have the Fahrenheit, which is measured in degree Fahrenheit. But in the course of this class, we are going to talk about these two, which are commonly asked in your exams. Now, for the Celsius and the Kelvin, we also have other units like what we call the Rankine. Rankine is one of the latest units for measuring temperature. So basically, in the course of this class, we are going to talk about Celsius and Kelvin, which is commonly asked in exams. So we have to look at how to convert Celsius to Kelvin or from Kelvin to Celsius. Again, we are learning this because you could be giving question in an exam where one is talking about Kelvin and the other is talking about Celsius, and we cannot work with them. We have to either convert the Celsius to Kelvin or the Kelvin to Celsius to make sure that they are the same. Now, so converting from Kelvin to Celsius, so let's take the first one, A. So from Kelvin to Celsius, what do we do? From Kelvin to Celsius, so Celsius is simply your value in Kelvin minus 273. So let's say we are given a question. Let's say a question 3 rather. So we have to convert let's say 400 Kelvin to Celsius scale. To Celsius. So to a temperature in Celsius. So we are going to convert 400 Kelvin, there's not like degree Kelvin, 400 Kelvin to a degree or to a temperature rather in the Celsius scale. So in Celsius, these are formulas. Celsius is what? Kelvin minus 273. So what are we going to do? So degree Celsius will be 400 minus 273. And when we subtract that, our final answer should leave us at 127 degrees Celsius. So this is the answer. So using this formula, I will be able to convert Kelvin to Celsius. So the equivalent of Celsius, of Kelvin rather than the Celsius scale is 127 degrees Celsius. So now let's come to the next one. The next one is how we can now convert Celsius to Kelvin. So let's go. So the B part of it, so let me put it at this point. So for the next, so B from Celsius to Kelvin. From Celsius to Kelvin, our formula K is degrees Celsius plus 273. So let's take this as a question. So question 4. So we have to convert 127 degrees Celsius to Kelvin. So let's go. So our formula K is degrees Celsius plus 273. So now let's go. So K is 127 plus 273. So what I want to do, we simply add them. So 127 plus 273 will eventually give us 400 Kelvin. So our value in Kelvin is 400 Kelvin. So basically, you ought to know how to convert from Celsius to Kelvin and then from Kelvin to Celsius. In one of our video lessons, I'll talk about how to convert even up to Fahrenheit and then to the Rankine scale. But for this video lesson, we are going to limit this video lesson to the Kelvin and the Celsius scale. Then the fourth thing we have is what we call amount, which is mole. So for amount, which is mole, so let's talk about amount. So when we talk about amount, is simply the given mass of a substance divided rather by the molar mass. So amount, so we have amount. So amount is simply defined as the ratio of the given mass or the reacting mass to the molar mass. So from that definition, we can draw up our formula. So amount is defined as given mass or reactive mass of molar mass. Though you might not really need this in solving questions, but what you ought to know in the course of this class is that we measure amount in mole, and it's presented with N. So whenever you see N in chemistry, it's saying that that is talking about amount of a substance. So let's add amount of a substance, which is measured in mole. So it's simply the ratio of the given mass to the molar mass. So the last thing we have is molar volume. And because of molar volume, we are going to talk about one very interesting concept which we call STP. So I wish to pay attention at this point. So we are going to talk about molar volume. So I have to draw molar volume from volume just to talk about it specially. So what is molar volume? So it's simple. From the name we can tell, molar volume. When we read it backward, it is the volume of 1 mole of that gas. So molar volume, which we are going to look at. So let's take the volume, the definition rather. So it's simply the volume. And when you talk about volume, remember from volume is the space occupied by 1 mole of a gas. So volume or the space occupied by 1 mole of a gas. So this is what we call molar volume at, there's something we didn't add, at STP. So now this brings us to this very interesting concept, which we refer to as STP. So I'll take a new marker and then we'll move on. So when we talk about STP, what do we mean? STP. Now STP stands for what we call standard temperature and pressure. So this is where the definition of STP comes from. It simply means standard temperature and pressure. So there is a system that has been agreed. So just imagine someone in Africa and then someone in Europe or in the Asia continent of the world. When they are working, they can work differently because, we are in Africa, for example, where things are different from probably the Asia or from the Europe. So things are different. So now be like, okay, how can we make sure that everything is working together? How can we make sure that we are doing this uniformly in quote? So ensure that whatever I'm doing is similar to whatever you are doing. So if I'm doing this, I'm rest assured that when you are doing it here, we are not going to have differences in our results. So they now came up with a standard, and that standard in measurement of temperature and measurement of pressure is what we call standard temperature and pressure. So it's a system that has been agreed upon. So scientists across the world in this field have come together and say, okay, let's agree on a particular temperature at which you can work and a particular pressure at which you can work to ensure that our result, irrespective of wherever we are, is the same. So that standard is what we refer to as the standard temperature and pressure, STP. Now the standard temperature in chemistry is 273 Kelvin, and standard pressure is what we refer to as 760 millimeters of mercury. Now for those writing various exams, more especially the UTME or the Jamb examination, I will advise you to know these parameters of heart, because why? In your exam you may not be given, so they are constant and they do not change, so they expect you to know it just as they are. So do well to know that the standard temperature is 273 Kelvin and the standard pressure is 760 millimeters mercury. So when you know this, you know peace. So now let's come to molar volume. Now the molar volume of a gas is simply the volume or the space occupied by molar 1 mole of that gas at STP. So at STP, so the molar volume of a gas at STP has a value, and that value is 22.4 dm cube, or in cm cube it is 22,400 centimeter cube. So note this again, these are not constant. So in your exam, if we told that a gas occupies a volume at STP, immediately you are told that the gas, 1 mole of that gas at STP, quickly remember that that volume of that gas at STP is what we refer to as the molar volume, and it has a constant or a value which is 22.4 dm cube or 22,400 cm cube. Again, in exam, you may not be given these parameters, so I will advise you to save them in your head. So then we are done with the various properties of a gas, from pressure, volume, temperature, and more importantly, amount of a substance. Then molar volume falls under volume, but I have to take it out just to explain this entire concept. So now we looked at the various conversion factors from pressure to volume down to temperature, and then there's a formula for amount which we refer to as given mass over molar mass, and then molar volume has a value which is 22.4 dm cube or 22,400 cm cube. So we then move on to look at gas laws proper. So let's go. So for the course of this class, we have spent just an hour, so we have 1 more to go. So we try to look at much gas laws that we can take in the course of this class. So let's go. So we'll list the various gas laws and we'll talk about them one after the other. So we have various gas laws in chemistry, various gas laws. So one of the first gas law, which is common to most things, is what we refer to as the Boyle's law. Then we have the Charles law. Then we have what we call the general gas law. Sometimes we call the general gas equation. So we have what we refer to as the ideal gas law. The ideal gas law. We have what we call the Graham's law of that. Or let's take Dalton's law before Graham's law. So we'll take Dalton's law of partial pressure. Dalton's law of partial pressure. So we have what we call the Graham's law of diffusion. Graham's law of diffusion. And lastly, but not the least, we have the Gay-Lussac law of combining volume. Okay, we'll just add one more to it, which we should call the Avogadro's law. The Avogadro's law. So these are the various gas laws we have in chemistry. So we are going to take them one after the other and look at some very core aspects and very important aspects as it relates to the Jamb and the WAEC examination. So they are the Boyle's law, the Charles law, the general gas equation, the ideal gas equation, the Dalton's law of partial pressure, the Graham's law of diffusion, which is very interesting law. We have the Gay-Lussac law of combining volume, and then the Avogadro's law. So we begin the gas laws by looking at Boyle's law. So let's go. So we'll start with Boyle's law. What's Boyle's law? And what makes Boyle's law Boyle's law? And what makes it interesting? So when we talk about Boyle's law, it's just simply a law that describes the relationship between two things. Those things are pressure and volume. Now recall that our definition for gas law says that gas law, they are just physical law or models that tells us the relationship between pressure, temperature, and volume. So what about Boyle's law? So let's go. So what's Boyle's law? So Boyle's law states that the volume of a given mass of gas, is inversely rather. So I will make this bold because this is confused to most students. Is inversely, or in capital letter rather, I'll write in capital letter, is inversely proportional to the pressure at constant temperature. So when we talk about Boyle's law, this is what the law states. Now for those persons that are writing WAEC examination, which is the SSC, I will simply advise you to do something, not just in this topic, but across all topics you meet in chemistry, in physics, in biology, and maybe other aspects where you have laws, I will advise you memorize all your laws, because there's something more common in WAEC. When you are given a question, probably it's a calculation question, Boyle's law. The question before that calculation question will most likely be state the Boyle's law. If it's Charles law, it will be state the Charles law. Or it could be in physics, probably they could tell you to state Hooke's law or state Ohm's law. Do you get? So it's very important you memorize your laws, and they tell us a lot. From your laws, you can eventually get your formulas. Now, what's Boyle's law? Boyle's law states that the volume, that's one of the properties of a gas, which we talked about earlier. So the volume of a given mass of gas is inversely, I have to make this in capital letters because most students usually think it's directly, some students think it's inversely, some students may not even know what to put at that point. So it is inversely proportional to the pressure. So the second property here is the pressure of the gas at a constant temperature. Now, what does this entire law tells us? When we talk about inversely, what do we mean? Inverse simply means as one thing is going up, the other one is coming down. So if one is increasing, the other one will tend to what? Decrease. And if this one is decreasing, this other one will start increasing. So when there's an increase, there will be a decrease in that side. And when there's an increase, there will be a decrease. So that's inverse. In mathematics, it's a very interesting topic, variation. So in inverse variation, an increase in one quantity leads to a decrease, and a decrease in one quantity leads to an increase. So what does that tell? It tells us that if we increase volume, the pressure will decrease. Or if we increase volume, if we decrease volume rather, the pressure will increase. Now let's take a good example. A good example is a balloon. You have a balloon. You have inflated the balloon. Then when you start pressing the balloon, what will happen? The air will start running out, and then the space inside the balloon will reduce. So I've increased pressure on the balloon. What have happened? Provided air can go out, I have decreased the volume of the balloon. Then when I blow it and I remove my hand, so I've removed pressure, the balloon becomes big, volume has increased. So it's just a two-way thing: increase in pressure, decrease in volume, decrease in pressure, increase in volume. So this is the entire scope of Boyle's law. Remember, at constant temperature, when we say constant temperature, the temperature is not changing. It means that what we are focused on is just volume and pressure. We are going to keep the temperature constant. So that's an easy way for you to identify that the question is on Boyle's law. You see a question talking about volume and pressure, and you are not told at the end at constant temperature. Just know that that question is simply on Boyle's law. So now let's get our formula, which is very important to us. Now the formula tells that volume inversely is 1 over whatever. So if I have 2, for example, the inverse of 2 is 1 over 2. If I have A, for example, the inverse of A is rather 1 over A. So volume is inverse proportional to P. The inverse of pressure is 1 over P. So this is the inverse variation of pressure to volume. So now in mathematics, we can't use this symbol, which we call variation. We call it variation or proportionality. We cannot use it to solve any question. So we are going to remove this and bring an equal to sign. So when I do that, I'm going to bring this in. And whenever you remove this sign and bring in equal to sign, you are going to add what we call a constant. That's, remember, constant temperature. You add a constant. Most times in math, they use K or they use C as constant most times. So we are going to use K over P. So remember, this is just a mathematical approach. Whenever you remove this sign of variation, we call it variation or proportionality sign, you are going to introduce an equal to sign and then a constant. In this case, we are choosing K over P. Then we cross multiply. When we cross multiply, P times U will give us PV. So we have PV is equal to K. So this is PV because K is a constant. It does not change whether on this aspect or on this other aspect. So whether in the first case or in the second case. So when we have the same constant, the same temperature, that's what we mean by the constant, in two different cases, we can therefore have P1 V1 is equal to P2 V2. So what do this stand for? So let's say we have a pressure and then we increase it. So we increase from P1 to P2. Something we definitely have to the pressure from V1 to V2. So P1 is referred to as the initial pressure. P2 is referred to as the final pressure. V1 is referred to as the initial volume. And lastly, V2 is referred to as the final volume. So in the first case, we look at the law which governs Boyle's law, or which governs the relationship between volume and pressure. So this is the mathematical expression giving us our formula, which is very important to us, which is P1 V1 is equal to P2 V2. So take note of this formula. So these are what they stand for. P1 is initial pressure, P2 is the final pressure, V1 is initial volume, and lastly V2 is the final volume. But before we look at calculations, there are graphs you must know. Very, very important. You must know these graphs. So let's take the graphs. So for the graphs, we have one common one. We can have this. Let's say we have a box. You could be given this illustration. We call it a graphical illustration. So let's say a graphical illustration of Boyle's law. Graphical illustration of Boyle's law. So you could give me something like this. Then we have P. We are going to take 4 P's. And then we have a bigger P. Then let's take a bigger V. Oh, let's make that bigger. V. We have another V here. Another V. And then another V. Now, don't mind this V. The V that shaking. Okay. Now, look at it. What was this? You could be giving this in an exam of which I have seen. Now you are giving some question. They could just ask you the graphical illustration or the diagram above illustrate what. And it's a simple question. A could be Charles' law, B Boyle's law, C whatever the option may be. But now it's a very easy thing to identify. When you are given a question like this and you see P and V, your mind should ask you which law talks about the relationship between pressure and volume. Obviously, that's Boyle's law. Another thing you find out is that you see this P is smaller, and then it increases in size from year to year. But V decreases in size. It could be the reverse. V could be here, P could be here. But what does that tell you? It tells you that as the pressure is increasing, the volume is decreasing. So again, remember the Boyle's law. Their pressure and volume are inversely proportional. They have this inverse relationship. As pressure is increasing, volume is decreasing. Or if pressure should decrease, volume will increase. So that inverse relationship is what we have as a graph on the board. So next, the other graphical illustration. So we look at this. We have something like this. We have something like this. So this pressure, and then this volume. Volume. We have pressure. Now, what does this tell us? Now look at something. Pressure could be as high as something. Then the pressure has dropped from year to year. So pressure has decreased. But what has happened to volume? If you trace to year volume, the volume has increased from year to year. So again, if you see a graph like this, they could ask you the graph above illustrate what? Again, if you see pressure and volume, you first think of Boyle's law. And also you see that it is gradually steeping. Another way you could be given is something like this. There are so many graphs to illustrate Boyle's law. So there's another graph that goes like this. This 1 over P. Let's take that 1 over P. And then let's take that as volume. And then you will be given something like this. Now, let's go back. Remember the formula from the very beginning, or the relationship. Now, there's another way we can interpret this. We can interpret this as volume is direct proportional to the inverse of pressure. So this and this, everything together, the inverse, that this is proportionality, they are direct proportional. And whenever you see a graph going like this, it tells you that that is direct proportionality. But don't mistake that for the law, which is Boyle's law. So this is not P anymore. It was in this case you had P and V. For this 1 over P. So we are taking everything together as one. So we are not saying volume is direct proportional to the inverse of pressure. So we can now have a graph like this. So there are so many graphs that illustrate Boyle's law. But more essentially, we can have this graphical illustration, this other graphical illustration, or this graphical illustration. So we'll take a question from the Jamb past question, and then we move to our next law, which is the Charles law. So if you are just joining us, or if you have been with us and you have any questions, try to leave your questions in the comment section somewhere beneath this video lesson. And if you are new here and you are not subscribed to this channel, you can please support us, encourage me by clicking the subscription button somewhere within the video, and I really appreciate that. So we'll take a question right now and then we forge ahead. So we'll take our fourth question. Our fourth question will be on Boyle's law, and this from the Jamb past question. So we'll take two questions just to have a good grasp of the Boyle's law. So question 1, or question 4 rather. Question 4 states that the pressure on 1000 cm3 of oxygen gas at 35 degrees Celsius is 750 millimeters of mercury. So it says what will be the volume of the gas what will be the volume of the gas what will be the volume of the gas if the pressure is increased to 1000 millimeters of mercury without changing the temperature. Without changing the temperature. Now A, we have it as 133.3 cm3. B, we have 85 cm3. C, we have 75 cm3. And D, we have 65 cm3. And this is a Jamb 1982 question. And this is question 3. So now we attempt this question so that we can have a proper grasp of what the Boyle's law is all about. Now when given a question, the first thing is don't panic. Read the question and ask yourself, where is this question coming from? Now, the question says the pressure of a gas on 1000 cm3 of oxygen at 35 degrees Celsius is 750 millimeters of mercury. Now, when you read this question, your mind should start telling that this question should be somewhere on gas laws, but where? Now, when you read the question, it says the pressure of a gas is at 35 degrees Celsius is 750 millimeters of mercury. So first of all, you can identify volume. Now, you may not be told that it's volume. Your unit should help you to identify that this is volume. Since cm3, first of all, should tell me that this question or this unit or this value is volume. Now, the pressure on 1000 cm3 of oxygen at this temperature, so they give us a temperature, is 750 millimeters of mercury. That's the pressure. The question is asking us what would be the volume. So that's the question. Please, the question. What would be the volume of the gas if the pressure is increased. So we increase the pressure to what? 1000 milliliters of mercury. So we increase it from 750 to 1000. So without changing the temperature, that's where the question lies. It says without changing. Meaning if you didn't change temperature, it means temperature is constant. Remember your Boyle's law at constant temperature. So this should ring a bell in your head and tell you that this is Boyle's law. So now we can go ahead and solve. So the initial volume is 1000 cm3. So V1 is 1000 cm3. At this temperature, which we obviously don't need. So in this case, if you are given a temperature in Boyle's law, don't bother using it because you don't have any place you are going to put it. Remember your formula, P1 V1 is equal to P2 V2. There is no space for temperature. So now the pressure, the pressure on this volume, which is 1000 cm3 of oxygen gas at the temperature is 750. So P1 initial pressure is 750 millimeters of mercury. So the question is saying what will be the volume if the pressure is increased? So V2 is what we are being asked to look for, and then the pressure P2 is increased to 1000 millimeters of mercury. So what is the formula? Since this has to do with Boyle's law, our formula for Boyle's law is simply P1 V1 is equal to P2 V2. Now in the case of WAEC, the first thing you should do is that you must change your subject formula. Very, very important. So since we are looking for V2, I'll make V2 to be such a formula. So for those writing WAEC, let's just take a further step. So since I'm looking for V2, I'll divide it by P2. So this P2 cancel P2. So V2 is equal to P1 V1 over P2. So in WAEC, it is ideal you make that thing you are looking for the subject of the formula. So since it's V2 because to P1 V1 over P2, just simply divide both sides by the thing closer to it, which is P2, divide, and we have this. So now we have this as, so V2 is equal to P1, and what's our P1 in this question? Our P1 is 750 millimeters of mercury. That's 750 times what's our V1? Our V1 is 1000 times 1000 all over what's our P2? Our P2 from the question is 1000 as well. So we have that as 1000. So we have P1 V1 is equal to P2 V2. I'm suspecting an error in the question, so we are going to alter something. We are simply going to alter the initial volume. The initial volume ought to be 100 cm3 for us to arrive at an answer. So we are going to alter that. So this is going to be altered to 100, not 1000. So we are going to alter this to 100. So when we do our calculation, 750 times 100 divided by 1000, V2, for us to have an answer among these options will be 75 cm3. So this is going to be the answer. There is probably an error somewhere in the question. So this should be 100, so this should be 100, and then this should be 100 for us to arrive at this option, which is 75. Because if we use 1000 to solve, the final volume will be 750, which is certainly not in the answer. So that is how we arrive at our answer. Now it's just a simple concept. You will see something. Coming back to the question, the pressure increased from 750 to 1000. Now from our calculation, V2 is 75 cm3, and we find out that volume has decreased from 100 to 75. There's a decrease. So it just simply tells us about Boyle's law. So an increase in pressure leads to a decrease in volume, and similarly, a decrease in pressure will lead to an increase in volume. So this is the entire concept of Boyle's law. So let's take another question for further understanding. So we'll take this question from the Jamb question 1991, question 5. So our second question, question 5, says that 30 cm cube of oxygen at 10 atmosphere is placed in a 20 cm cube container when it says calculate the new pressure if the temperature is kept constant. If the temperature is kept constant. Now this is a Jamb 1991. Okay, so let's take the options. Option A, we have 6.7 ATM. B, we have 15.0 ATM. C, we have 6.0 ATM. And then D, we have 66.0 ATM. So this is the fifth question we are going to take in the course of this class. So the question reads, 30 cm cube of oxygen at 10 atmosphere. Atmosphere is what we refer to as ATM in the short form, ATM. So that's ATM. So it's placed in a 20 cm cube container. Now you observe something. The volume has decreased from 30 to 20. The question says calculate the new pressure if the temperature is kept constant. Now what has given this question away is that they have told us that the temperature is constant. Again, that takes us back to our Boyle's law. We say that volume and pressure are inversely related at constant temperature. So we are going to identify our parameters. Initially, we had a volume of 30 cm cube. So V1 is 30 cm cube. At 10 ATM, ATM is our initial pressure. P1 is 10 ATM. It's placed in a 20 cm cube container. So that's our V2, 20 cm cube. Now, it says calculate our new pressure. So sometimes what we call initial will be old, and then what we call final will be new. So we can say that V1 is old volume, P1 is old pressure, V2 is new volume, then P2 can be the new pressure, which we are looking for in this case. So again, we are going to ask ourselves, what is our formula that has to do with Boyle's law? So we know that P1 V1 is equal to P2 V2. So what's our P1 in this question? P1 is 10 ATM. Again, just to add, before solving any question, ensure your units are the same. That's why I gave you the various conversion factors in terms of pressure, in terms of volume, and in terms of temperature. So before solving any question, ensure the units are the same. For example, this is cm cube, this is cm cube, we are good to go. This is ATM, and then when you look at your options, they are in ATM, so you can proceed. But if there's any disparity or there's any difference, you must convert one to the other. It's very important. So now let's go. We are looking for P2. For the sake of those writing WAEC again, we are going to make P2 the subject of the formula. So since we are looking for P2, I'll divide both sides by the other entity, which is V2. So the other side by V2 in this case. So V2 cancel V2. So therefore P2 is equal to everything here. P1 V1 over V2. So let's go. So P2 is equal to P1 from the question is 10 ATM. 10 times V1 from the question is 30 cm cube over V2 from the question is 20 cm cube. That's over 20. So we are going to divide 10 times 30. That goes 300 divided by 20. That goes 15. So therefore P2 is equal to 15 ATM. So this is the answer to that question. So we can obviously see something. Let's play. So this is 15 ATM. Now you can see that, let's take this off so that I can explain something. V1 to V2, 30 to 20, volume has decreased. That means that we expect an increase in pressure. That's why you see that from 10 to 15, there's an increase. So a decrease in volume, an increase in pressure. So this just simplify the Boyle's law we have been talking about. So if you got value from this video, or you have questions, any comment suggestion, again, do it to leave them in the comment section somewhere around this video lesson. And if you haven't subscribed to this channel, I will please implore or beg you to please help us subscribe to the channel, as this will go a long way in helping this channel. So this is Boyle's law, which we have looked at, and in essence, you should know the law which tells us that pressure and volume are inversely related at a constant temperature, and then know your formulas, or formula rather, which is P1V1 is equal to P2V2, and then know the graphical illustration which we looked at in the earliest part of this law, which is the Boyle's law. So we move on to look at the second law, which is Charles' law. So we are looking at the third one, second rather, which is Charles' law. So the third law we are interested in is Charles' law. So what's Charles' law, or what does it state? A very beautiful law. So let's go see. Charles' law states that the volume, again volume, of a given mass of gas is directly proportional to the temperature at constant pressure. So the temperature at constant pressure. So Charles' law is a very special law. Again, the law tells us the relationship between pressure, volume, and temperature. So now when we look at Charles' law plays with two crucial properties of a gas. Now it tells us that the volume, so the first is the volume of a given mass of gas is directly, I want to place that in capital letters. So I will alter that and change that to capital letter, directly. So you should know this. When you talk about Boyle's law, remember it is inversely between pressure and volume. When we talk about Charles' law, the direct relationship between volume and the second, which is temperature at constant pressure. So in this case, we really have nothing to do with pressure. So when you are given a question and you get to see at a point, you are being told that at constant pressure, start thinking of Charles' law. So let's play with this entire guy. So the law tells that volume is direct proportional. So that's the sign for proportionality. Direct proportional, they should just be on the same line. So T. So this is direct proportional. And what does this mean? When we say direct proportional, what does it mean? We already know what inverse means. When there's an increase, there's a decrease on the other side. And when there's a decrease here, there's an increase on the other side. But for direct proportionality, direct proportionality simply means as I increase, you should also increase. That's simple. And if anything should make one to decrease, the other should also decrease. So in essence, an increase in volume or an increase in temperature will lead to an increase in volume. And if there's a decrease in volume, there will also be a decrease in pressure. So that's simply direct proportionality. A good example is, let's use a kettle. We have a kettle and you're boiling water in the kettle. When you start heating the water, it will get to a point, the kettle is so hot, the water particles, they have turned to gas, they want to evaporate. You will see that they want to push the lid, like they want to push the lid out of that kettle. You see that the lid is trying to leave. Why? Because the gas wants to expand. When you increase temperature, the particles will now gain more kinetic energy and they want to expand and fill everywhere. So when you increase temperature, just like you give a child food, the child will start playing, jumping up and down. Why? So that food is temperature. The child is jumping from one place to another. The child is occupying a lot of spaces. That is volume. So if the child becomes hungry, temperature has dropped, the child will just stay in one place. Volume will decrease. So just a simple relationship. Increasing volume, increasing temperature. Decreasing volume, decreasing temperature. So that's just simple. So again, in maths, we cannot use this to solve. Rather, we are going to remove it and introduce an equality sign. So when we do that, we add a constant kt. But we want to make these two guys to be on one side. So we'll divide both sides by t, divide by t. So t will cancel t. So therefore, I have v over t is equal to k. So we now have this. Now with the same constant on two different locations, initial and final, or old and new, I'm going to have v1 over t1. So the formula becomes v1 over t1 is equal to v2 over t2. So this is the formula we use in Charles' law. So with the same constant on two different locations, initial and final, or old and new, I'm going to have v1 over t1 is equal to v2 over t2. Now, the next thing we are going to look at are graphical illustrations. So let's take one before we solve questions. So you will tend to see something like this. Let's take this. So we could have v, and then let's say we have v. We could have t. Now, what can you see from this graphical illustration? You can be given this question in exam and you'll be asked, this illustrates what? You obviously see that v is increasing, t is also increasing. So they are both increasing. If v should decrease, t will likewise decrease. So that is just a direct variation. So as I increase, you increase. Simple. Then if one should decrease, the other will also decrease. So let's look at another graphical illustration, a very common one, commonly asked in exam. You'll be given a graph like this, then so this volume, then this temperature, you are measuring in degrees Celsius. The issue is that at 0 Kelvin is equal to minus, so this 0 Kelvin, let's take it here. So 0 Kelvin is equal to minus 273 degrees Celsius. So we are using the Celsius scale. So this is 0, minus should be at the negative x. So this is where you have minus 273. Again, it's very easy to identify an exam. Once you tend to see volume and you tend to see temperature, you should start thinking of Charles' law. And you can see that the graph goes like this. It means that volume is increasing, temperature is also increasing. So there is this direct relationship between volume and temperature. So this is just the graphical illustration, and then this is the formula we use in Charles' law. So we are going to look at some few questions, and then we'll move to our third equation or our third law, which is the general gas equation. So let's take a question here and then move on. So our sixth question reads, question 6, and the sixth question says a gas sample with initial volume of 3.25 dm3 is heated and allowed to expand to 9.75 dm3. It's allowed to expand to 9.75 dm3 at constant temperature or at constant pressure. At constant pressure, what is the ratio of the final absolute temperature what's the ratio of the final absolute temperature to the initial absolute temperature? question, and we are going to take the options. Option A we have here is 3:1, B is 5:2, C is 5:4, and then D is 8:3. And this is a UTME question, 1995, question 15. So this is the question we are going to attempt right now. And what we have for this question is a very simple question, though it's just set in a different pattern. But let's read the question. The question says a gas sample, already that you should be thinking of gas, more especially gas law in this case, with initial volume of 3.25 dm³ is heated and allowed to expand to 9.75. So the volume has increased from 3.25 to 9.75 at a constant pressure. Again, this should be a giveaway. At constant temperature, we should start thinking of Charles' law. The question says, what is the ratio of the final absolute temperature to the initial absolute temperature? Now, it's a very easy question. So since it's Charles' law, we are simply going to ask ourselves, what's the formula? So the formula is V1 over T1 is equal to V2 over T2. So this is the formula from Charles' law. Now, the question is very logical in the sense that it says, what's the ratio of the final to the initial? So it's final. Final means our final temperature is what we call T2 ratio T1. Now in mathematics, we can write this as T2 ratio also means, this ratio also means division over T1. So we are going to arrange this equation in such a way that it's going to resemble T2 over T1. Again, I will explain. The question is different from what we might be expecting. It says, what is the ratio of the final absolute temperature? Final is T2. Remember, T1 is initial. So ratio of T2 to the initial, which is T1. Now, ratio in mass means division. It's like T2 over T1. So like I said, we are going to arrange this equation. Just imagine you are playing puzzle. We are going to arrange it such that it's going to resemble T2 over T1. So the first thing I'll do is that I'll cross multiply. So we'll cross multiply. When I cross multiply, V1 times T2 give us V1 T2. Then V2 times T1 give us V2 T1. Then next thing we'll do is that we remember we are going to arrange it as T2 up and T1 down. So the best thing I'll do is that I'll divide both sides by T1 and divide by T1. So at the end of the day, I'm going to have T2 over T1. But if you divide by T2, you are going to end up having T1 over T2. Remember, what we need is T2 over T1. Also, I'm going to remove this V1 from here. So divide both sides by V1, V1. So what is going to happen is that V1 will cancel out V1, then T1 cancel out T1. Then on this side I have T2 over T1 is equal to, on this side I have V2 over V1. So let's go. So now I'm going to write this up. T2 over T1 is equal to V2 over V1. So if you just see something, you'll notice that 2, 2, 1, 1 directly proportional, direct proportional. So let's go. T2 over T1 is equal to, what are V2 from the question? Remember, this is the initial V1. This is V1. Then this is final V2. So V2 is 9.75, and then T1 or V1 rather is 3.25. Then we are going to divide. So we are going to see how we can divide this and this to give us, to suit any of these options. So let's try dividing and see what we can get. So 9.25 divided by 3.25, 3 can divide both of, sorry, 3.25 can divide both of them. And when this is divided by 3.25, we are going to have 3. When you divide by 3.25, we are going to have 1. So T2 ratio 2:1 is equal to 3 ratio 1. So that brings our answer to option A, which is 3 ratio 1. Again, this is just a very important, crucial, and logical question in the sense that you just want to test your knowledge on ratio. So when you solve, it's going to be 3 ratio 1. Now be mindful, especially for those writing the UTME or the Jamb examination. In questions like this, they could trick you and they could put options like A, 3 ratio 1. In fact, most times the wrong answer could come first. Let's say A, 1 ratio 3. And then B could just be 3 ratio 1. And C could just be, let's say, 2 ratio 3. and D could just be 5:2. Now some students will be confused and say, oh, 1:3 and 3:1 they are the same. They may end up picking this, which is wrong. The question specifically asks you ratio of final to initial, and final to initial is 3:1. If you write as 1:3, you are saying initial to final, meaning you are going against the original question. So please, when you come across that question, be very mindful and very careful when you are picking answers to questions like that. So let's take a second question on chart so I can understand it better. So question 7, which is our 7th question. So our 7th question here reads, let's take that on Charles law again. So while I'm writing the question, you can always do it to attempt it, so and see if you can probably get it before we solve the question. So let's take this question. The question says 28.8 cm3 of nitrogen gas. 28.8 cm3 of nitrogen gas. 0.8 cm3 of nitrogen gas at 15 degrees Celsius is cooled to 0 degrees Celsius at constant pressure. At constant pressure, the new volume of nitrogen is, now we have various options. Option A is 17.4 cm3, B is 14.7 cm3, C is 27.3 cm3, and then D is 31.7 cm3. Now this is a Jamb question, Jamb 1981, question 30. So that's the question we are going to attempt in this part of this video. Now we have a question. The question again reads 28.8 cm3 of nitrogen gas. Now in some exam, you may not be told that this is volume, this is temperature, and this is pressure. The ability to use the units to find that is very, very key. Now, since we are told that this is cm cube, I should know that this is volume. So V1 is equal to 28.8 cm cube of nitrogen gas at 15 degrees Celsius. Celsius is used for measuring temperature. So I should go to decify this as temperature. So T1 is 15 degrees Celsius. Now the gas was cooled or is cooled to 0 degrees Celsius. So T2 is 0 degrees Celsius at constant pressure. Now this one makes it easier for us to know that at constant pressure makes it easier for us to know that this is Charles law. So the new volume, that is V2 of nitrogen, is what? So now this is a giveaway question. One, based on the fact that the question tries to relate volume and temperature, and also somewhere within the question we are told that it is at constant pressure. So what's our formula? But before we use that formula, there's something I want you to know, very important. So if you are taking a note, just write this down. Whenever you are given a temperature in Celsius, anywhere, not just in Charles law, if you meet it in general gas equation, in ideal gas equation, whenever you are given a question in Celsius, never use it to solve. Never use it to solve. You must convert that Celsius to Kelvin. So it's a must, always. So let's take it down. Always ensure your unit, or the unit, let's be more specific, the unit for temperature is in Kelvin. For temperature is in Kelvin, before solving gas laws question. Very important. Before before solving gas law questions. So this is a very important thing that most students might just miss out in exam, and then they will be so confused as to my answer is not in the options. Now it's a very fundamental principle you must know, because our standard temperature, if you should remember, is measured in 273 Kelvin, and the unit here is Kelvin. So always ensure that the unit for temperature before you solve any gas law question is in Kelvin. I'm emphasizing this for the purpose of other laws we are going to encounter, like the general gas equation, periodic gas equation, and the others. Now let's come back to the question. What is our formula? Our formula is V1 over T1 is equal to V2 over T2. So this is the formula for solving questions related to Charles law. So again, for the sake of those writing WAEC, it is ideal you ensure that that unknown is made the subject of the formula. So since we are looking for V2, let's cross multiply. 1 cross multiply, V2 times 2 and give us V2 T1, then V1 times T2 give us V1 T2. Now I'm looking for V2, so I'm going to divide both sides by T1 divided by T1. So T1 will cancel T1. So our formula for those in writing WAEC, very important. You must do this. You must write this out on your screen, because each part is a mark. There's a mark allocated for each part. So this is V1 T2 over T1. So let's come to our parameters and get our options. So our parameters here, so V1 is equal to V1 from our parameter here is 28.8 times T2 is 0. But again, this where this comes or becomes relevant. So I'm going to convert to Celsius. It's simple, just add 273, and this will give us 273 Kelvin. Similarly, this we are going to add 273, and then this should give us 8, and then that's going to be 2 rather. So this will give us 298 Kelvin. So please and please, whenever you see the unit for temperature in Celsius, quickly convert that temperature from Celsius to the Kelvin scale and be safe. So our T2 is this, which we just converted to 273 over T1, which is 288. So we are going to just do a little multiplication and division. So I'm going to multiply this with this, and then our answer I'm going to divide it with 288. So let's go and see if we can get an answer to this question. Times 273 divided by 288, and that gives us some 27.3 centimeter cube. So this is the answer to this question. So when you apply a formula for solving question on Charles law, we are going to end up getting 27.3 Kelvin. Again, the rule is simple and it's basic. Don't forget this point, because most of them might miss it as an exam. At the end of the day, if you use 0 in calculating, let's say at around when you use 0, your entire answer will become 0. Because 0 times this entire guy will give us 0. So that will just change this entire answer to 0, and you will clearly see that none of the options here have an answer to be 0. So don't forget that whenever you are giving any of your units in Celsius or maybe another thing, maybe Fahrenheit, Rankine, bring it back to Kelvin. So let's look at the very last law for the purpose of time and this class. So we are going to look at general gas equation. So and then we'll look at the rest laws in subsequent class. So we'll look at the general gas equation. So general gas equation. So these are third law. So one thing you ought to know is that general gas equation is a combination of Boyle's law and Charles law. It's a combination of Boyle's and Charles law. So this is a combination of so that's why it's called general. It takes both laws together, brings them together. So it combines both Boyle's and Charles law. So we are going to state Boyle's law and Charles law and then merge them together. So let's go. So from Boyle's law, it states that remember Boyle's told us that volume is inverse proportional to pressure, but Charles told us that volume is proportional to temperature. So look at something from Boyle's law. We have that volume is inverse proportional to pressure. Then from Charles, we have it that volume is proportional to temperature. So in both of them, they both have volume. So we are just going to merge them together. So we'll begin with the Charles part of this law. So from here, we have that volume is proportional to temperature. So it states that volume is proportional to temperature. Proportional to temperature. Proportional to temperature. This and so we are done with this. Volume is proportional to temperature. Then this is left, and it's inverse proportional to pressure because remember in both of them they both share volume. So you get to see volume in both equations. So they are proportional to temperature and inverse proportional to pressure and inversely proportional to pressure. So this is just a combination of Boyle's law and Charles law. Now what we just want to know is in which you have just combined them. In both of them you see volume. So from here volume is proportional to temperature, from here volume is inverse proportional to pressure. So that's just a combination of Boyle's law and Charles law, and that brings us to general gas equation. So what is more important to us here is our formula for calculating question. So already we've explained the entire concept of Boyle's law, and I've also explained the entire concept of Charles law. So let's derive the equation for the general gas law. So I'm going to the general gas law, general gas equation. Now from this entire write-up, what they both share is volume. So volume, first of all, is proportional to temperature. So we have volume is proportional to temperature, and inversely proportional to what? Pressure, so over P. So this is what we have. So from this, remember, we cannot use this to solve. We are going to remove this and introduce an equality sign. So V is equal to, and when you bring this, you must bring a constant K T over P. So we are now good to go. So you cross multiply, P times V will give us PV is equal to KT. So divide both sides by T. This will cancel this. Then when it cancels, we now have PV over T is equal to K. Then on two different occasions, P1, V1, or initial and final, I now have P1, V1 over T1 is equal to P2, V2 over T2. So this is what we refer to as the general gas equation. So remember, it's just a combination of Charles law, volume is proportional to temperature, and the combination of what? Boyle's law, volume is inverse proportional to pressure. So remember, remove this and add the equality sign, and in doing so, add a constant, then this remains T over P. Then cross multiply, we have PV is equal to what's left here is KT. But we just want to ensure that our parameters are taken to one side. And now have PV over T is equal to K. So that's where we have this. So on two different occasions, time one or initial and final, I have P1 V1 over T1 is equal to P2 V2 over V2. So we'll take a question, and then that brings us to the end of this video lesson. So let's take our final question, and that should be question 8. For question 7, so question on Charles law. So we take that. Okay, so we'll take this question. So question 8 or 7, as the case may be, we have it as 200 cm cube
Don't go to carry any task now. And they go sleep. Now you can put cloth under the door, yeah.
So we have these are the question and then these are the options. A is 342.53 millimeters of mercury. B, we have it as 1430.54 millimeters of mercury. C, we have it as 467.11 millimeters of mercury. And then we have option D has 400 millimeters of mercury. So this is a Jamb question, 2014 question 5. So that's the Jamb question, 2014 question 5. So we are going to attempt the question and then forge ahead. So reading this question, you find out that 3 things are talked about in the question. You can see cm cube, which tells us that the question is talking about volume. You can see temperature. Temperature appearing twice is not constant. 25 and 75 is not constant. So we have temperature. You can also see pressure, millimeters of mercury, and even in the ocean. So we can tell that there's pressure, there's volume, and there's temperature. Once you see these 3 things being involved and known is constant, you should start thinking of the general gas law. So how are we going to apply this in solving question? So you just write out your parameters. So we have 200 cm cube initial volume or the old volume. So V1 is 200 cm cube of a gas at 25 degrees Celsius. So T1 is 25 degrees Celsius. Remember, never use the temperature in Celsius to solve. Convert it to Kelvin, which we'll do later. So it exerts a pressure of 700 millimeters of mercury. So P1 is 700 millimeters of mercury. Calculate its pressure, P2, calculate. If the volume, V2, increases to 350, so if the volume rather increases to 350, so we have it as 350 cm cube. At that temperature, T2 is 75 degrees Celsius. Again, always ensure your units are uniform. So volume is in cm cube, yes, in cm cube here, so we are good. So pressure is in millimeters of mercury, and when you look at your options, it's also in millimeters of mercury, we are good. Now temperature is in both Celsius and Celsius. We would have been good, but we can't use to solve, so we have to convert it to Kelvin. So remember, add 273, then add 273. So let's see what the value will be. So we have 25 plus 273, and that will give us 298 Kelvin. Then for this we have 75 plus 273, and that will give us 348 Kelvin. Now what's our formula for the general gas law? We know it to be P1 V1 over T1 is equal to P2 V2 over T2. But we are looking for P2 in this case, so we are going to make P2 equal to a formula. So let's cross multiply. So P2, let's cross multiply. So this times T1, we are going to have P2 V2 T1 is equal to, then this times this, I'm going to have P1 V1 T2. Since I'm looking for P2, I'm going to divide this with this other expression close to it, V2 T1 divided by V2 T1. So this will take off this. So we now have P2, which we are looking for to be P1 V1 T2 over V2 T1. So we can now calculate. P2 is equal to P1, and P1 is 700 times V1. V1 is 200 times T2, which we have here as 348, divided by V2, which is 350, times we have T1, which is 298. So I'll calculate and then I'll write your answer up here. So P2, which we are looking for, will be So we are going to multiply this numerator, multiply the denominator, and then divide both of them. So let's go. So we have 700 times 200 times 348 divided by 350 divided by 298, and that will give us 467.11 millimeters of mercury. So this is the final answer. Again, general gas equation, general gas law is just simply a combination of the Boyle's law and the general gas law. So it's just a simple combination. So we are talking about the three properties of a gas: pressure, volume, and temperature within this equation. So viewers, I hope you enjoyed this video lesson and you also learned something richly from this video lesson. So do it to give this video lesson a thumbs up, and also if you have any question, comment, or suggestion, do it to leave them in the comment section somewhere beneath this video lesson. And if you haven't subscribed to this channel, I urge you to please subscribe to this channel, and this will go a long way in encouraging and supporting us to creating more videos. So do have a wonderful night rest or a daytime, depending on whenever this video gets to you, and have a wonderful time. See you in my next class.